Okay, so in this session, we're going to do a brief summary of electrophysiology. So when we want to think about the heart as a whole, contractile cells, or the myocytes, they make up about 99% of the cardiac muscle cells. And they do the work of, or the mechanical work of pumping blood around the body, whether that's from the left ventricle to the general circulation, the right ventricle to the pulmonary system, or whether it's from the atria into the ventricles themselves. It's all about pumping blood around the body, so to speak. But what stimulates that in the first place? What causes the atria to contract and what causes the ventricles to contract? Well, it's actually changes in electrical currents within those cells. So you know, from other systems, you're thinking about calcium binding to actin, myosin. In the case of the heart, troponin complexes. You have these complexes that are causing contraction of the muscles. And where does all this electrical current actually start within the heart itself? Well, it begins in what's called the pacemaker, or the sinoatrial node. And this is shown in this diagram at the bottom. The sinoatrial node is present within the right atria. And this area, this little selection of cells within the SA node, they have autorhythmicity. And what that means is that they generate action potentials automatically. So they generate them. If you think if your heart rate is 60 beats per minute, these autorhythmic cells are generating an action potential or a set of action potentials every second. So you get 60 of them per minute. So these rhythmic contractions of the heart are maintained by the electrical signals that are generated in the heart itself. Okay, and that's unlike the skeletal muscle, as you know. They do not do the contraction themselves. That's the muscle myocytes. Remember that they make up about 99% of the cells. These are more specialized because they initiate and they conduct action potentials, which then transfers that electrical potential, that electrical activity into the myocytes, to the myocytes more specifically, causing the myocytes to open various voltage-gated channels and therefore leading to calcium influx and generation of contraction and relaxation of your myocytes. So that's what this whole process is about. And of course, we know that the heart rate changes and the strength of contractions change. And that is all helped to be regulated through the autonomic nervous system. Remembering the autonomic nervous system consists of the sympathetic, which is the fight or flight, and the parasympathetic, which is the rest and digest. And so what we can do to these autorhythmic cells and to other cells within the electrical conductance pathway, we can do what's called chronotropism. In other words, we can change the rates, like a clock, chronotropism. So we can change the rate, and the sympathetic nervous system, for example, will increase the permeability to calcium and sodium and other ions, allowing them to diffuse down their concentrations gradients quicker, and therefore stimulating these action potentials quicker. And so that generates more action potentials and therefore a greater heart rate. And the parasympathetic nervous system, as you would expect, slows it down. You've then got inotropism, and that changes the contractility. Okay, so the sympathetic nervous system activates myocytes, increasing their contractility, the strength at which they can contract. And if they contract harder, they squeeze more blood out with each heartbeat, with each contraction. And that again is stimulated by the sympathetic nervous system, not really altered by the parasympathetic nervous system. And the last one is dromotropism, and that's just change in conduction speed. So not the rate, but the speed of that conduction through the electrical system, and the sympathetic nervous system increases its permeability and therefore increases speed, and the parasympathetic slows it down, primarily at the next point in the pathway from the SA node, which when the electrical current passes from the SA node through the atria, following these little arrows, it comes to this little point, the AV node. And we can get a little block there, a parasympathetic block. It slows at this area down, this little area down, before the conductance goes into the ventricles themselves. And so, like I said, the spread of the cardiac excitation, it starts at the SA node in the right atria, spreads throughout the atria, so through into the left atria and in the right atria, and spreads cell to cell from myocyte to myocyte. So whilst it starts in specialized autorhythmic cells in the SA node, it spreads throughout the atria from myocyte to myocyte. And this is called your interatrial pathway, extending from the SA node to the right atria and to the left atria. And this, because the atria are quite small, and that spread is about 0.5 meters per second through myocytes themselves, it ensures that a wave of excitation can spread across the left atria at the same time excitation is similarly spreading across and throughout the right atria. And so it just ensures that the two atria become depolarized to contract at the same time. Like I said, it spreads at about 0.5 meters per second through myocytes. We have then the internodal pathway, and this is the only way that electrical activity can spread from the atria to the ventricles, because the rest of the connections are through non-conductive fibrous tissue. And so the action potential, remember, starts at the SA node and it gets to the AV node after about 30 milliseconds, remember, from myocyte to myocyte across this small little distance. And so, like I said, that's about 0.5 meters per second, and the whole time it takes about 30 milliseconds to spread from the SA node to the AV node. And that is sufficiently fast for the atrial spread cells to contract simultaneously. And then when the electrical conductance gets to the AV node, there's a delay. And there's a delay of about 100 milliseconds. And that just allows the atria to fully contract before, and therefore the ventricles to fill, before the electrical current starts to spread throughout the ventricles and causes the ventricles to contract. So, once we've got to the AV node here, the impulse travels very rapidly down the septum, so down there, and the left and right branches of the bundle of His, and then throughout the Purkinje fibres, which are surrounding and engulfing around the entire ventricle mass. Remembering the ventricular mass is in 3D and this image is in 2D, so you can just see it going there, but of course it's all the way over the top and around the bottom of the ventricles as well. But the ventricular mass is much larger than that of the atria, so therefore it doesn't spread throughout the mass of the ventricles through myocytes, because as we've said, that is about 0.5 meters per second, and that's just not fast enough. Okay, it is fast enough for the atria, but it's not for the ventricles. Because if the entire ventricular depolarization process through the entire huge bulk of that ventricle was spread through myocytes, you'd have the myocytes contracting at different points, at different times, and you want the ventricular mass to contract as one. And you want that for efficient pumping. So like I said, the impulses enter the ventricle at the bundle of His, then through the left and right bundle branches, and these very specialized and wide electrical current areas, if you like, allow much faster contraction. So through the bundle of His, you're going at 2 meters per second. Through the bundle branches there, you're going at 2 meters per second, and then the Purkinje fibers are at 4 meters per second. Notice how slow it is through the AV node. Remember there's a pause there, and so that pause, you can see it's traveling at 0.05 meters per second. So it's very, very slow, and that's what that pause is there for. And so what this means, because the electrical current can flow through the bundle of His, bundle branches, and the Purkinje fibers so fast, the impulses are transmitted throughout the entire ventricular mass within about 30 milliseconds, which means that they can then go on to contract simultaneously, depolarize and then contract simultaneously, and that's exactly what you want. So what happens if it goes wrong? Well, remember, we've got our SA nodes. These are the specialized non-contractile cells with autorhythmicity, and these are the ones that we call the pacemaker, because these are the ones that take control in health. But we do have them in lots of other little places. We have them at various spots throughout the atria. We have them at the AV node. We had them in the bundle of His and the Purkinje fibers. But they all contract or have that autorhythmicity, at different times, at different speeds, if you like. So if we're getting about 60 beats per minute or action potentials per minute at the SA node, it's slower at the AV node and slower at the bundle of His. Okay, and the actual speed is about, like we said, about 70 to 80 at the SA node, so that if your heart rate is 70, then you're having 70 action potentials per minute there. If you have a heart rate of 40 beats per minute, then you are getting 40 sets of action potentials coming from the SA node per minute. but on average it's something like 70 to 80. Okay, and then remember, we also have these autorhythmic cells at the AV nodes near the base of the atrium, near the septum. And this is slower at about 50 beats per minute. And then the bundle of His is about 20 to 40, so 30 beats per minute. And again, throughout the Purkinje fibres, this is about 30 beats per minute. But what does this actually mean? Or why do all of these cells have different rates of slow depolarization? Well, the SA node are the fastest to decay, and the bundle of His and the Purkinje fibres are the slowest. And what that means is the SA node is the natural pacemaker of the heart and drives the rest of the heart at this rate. In other words, the entire heart becomes excited, triggering the contractile cells to contract and the heart to beat at the rate set by the SA node. The others can't assume their own natural slower rate because they're activated by action and potentials that have originated in the SA node, and they're getting there before they can reach threshold at their own much slower rhythm. So what does that mean if the SA node fails? Well, if the SA node fails, then the AV node takes over because it is the next fastest one. There'll still be contraction of the atria, but it'll likely lose rhythm because there are subsidiary pacemaker cells throughout the atria that can generate electrical impulses and trigger atrial contractions. But again, these are slower. And so basically coordination between the atria and ventricles will be lost, and atrial bradycardia, so slowing of the heart rate, develops if the SA node fails. So as the AV node cells, as we said, as the AV node cells are so slow, a pacemaker may need to be provided to allow the atria and ventricles to act in a coordinated fashion. And when you hear about people having heart pacemakers, they're basically getting a fake SA node, something that contracts or stimulates electrical activity, at roughly the rate that the SA node would. So, like I said, what happens if it goes wrong? Well, the SA node we know is innervated by the parasympathetic nervous system and the sympathetic nervous system. And the balance between these systems controls the pacemaker rate. Parasympathetic input via the vagus nerve decreases, SA node pacemaker is dominant at rest. Whereas sympathetic nerve input, as well as because of the release of adrenaline from your adrenal medulla, for example, during exercise and stress, increases the heart rate and increases SA node action. So SA node malfunction, lots of things can cause this. Local cardiac diseases, systemic diseases that involve the heart. Some toxins can do it, and drugs. They can alter SA node function. So what I want you to think about is what happens if these autorhythmic cells fail. So in general, the next fastest autorhythmic cells take over. So under normal circumstances, and hopefully you're all nice and healthy with a normal SA node, and your SA node sets the pace at 70 to 80 action potentials per minute, so 70 to 80 beats per minute. And yours might be slower, or it might be faster, but that's crudely how it sets the pace. What happens, so press pause and have a little bit of a think, what happens if the SA node becomes non-functional? And what happens if the AV node becomes non-functional? So, if the SA node doesn't become functional, the AV node takes over, and so you'll have a slower pace. And on average, that's 40 to 60 action potentials per minute. And so what that means is you might have inappropriately slow ventricular rates and long pauses at rest or during various stresses. So remember, your ventricle is now going at 40 or 50 instead of 70 to 80. So it's not as fast as it should be. And the heart doesn't respond as well to various stressors because it's not responding as well to sympathetic nervous system activation, which largely works through the SA node. And the SA node isn't working, of course. And what happens if the AV node isn't working? Well, the atrium can still work fine, okay? So if the AV node isn't functioning but the SA node is, that's still working absolutely fine at 70 to 80 action potentials per minute. But the ventricles aren't getting that information from the AV node, so they now contract at the bundle of His fibre rate, which is 30 action potentials per minute. So basically you're getting the atria contracting at 70 to 80 and the ventricles completely in a discoordinated way, so in other words, not interacting with the atria, contracting at 30 or so action potentials or beats per minute. And if there's a complete block between the two, so the AV node completely doesn't work, that's called complete heart block. And if there's a bit of a long pause, a bit too long, then you get a partial heart block. So you get different types of heart block. But of course, if you have a ventricular rate of 30 beats per minute in most people, this will only support a very sedentary existence. In fact, most people will become comatose.